Within signal processing, audio processing is really, really cool. Lots of fun. Let's dig into some of the details of one of my favorite audio effects. This is the echo. That's a cool one. Okay, what is an echo? How do you write this as a dynamical system? This can be written as a kth order recurrence relation on a digital signal. Something of the form xn plus 1 equals alpha times xn minus k plus 1 plus u sub n. Now, what is this alpha? This alpha is a gain. It is a constant somewhere between 0 and 1. You don't want to make that guy too big. The u sub n term, of course, is the user input. It's the signal that you feed into an echoplex. And the x is the output signal. It's the thing that you get out from that. Now, this recurrence relation can be vectorized, can be put into a matrix vector form like we just considered. And the way that we do this is through that sliding window. And what we get is the system EX equals some matrix times X plus this user input signal. And what is this matrix? It has a nice block form where it has zeros in the last column, first row, a k-1 by k-1 identity matrix below that diagonal, and then in the upper right-hand corner, an alpha. You should check that multiplying this out gives you exactly that kth order recurrence relation above. So then, does this make sense? Well, let's think about it. If alpha is between 0 and 1, and if k, the order of this recurrence, is sufficiently large, then let's consider a simple example where our user input signal u is something like a chirp, or, I don't know, like a hand clap, something like that. If I draw out what that signal looks like over time, then I have this spike. And if I think about the effect that running this system has on the output signal x, then what happens? We're always feeding u into the next slot of x, and then we're processing by adding alpha times what happened k steps before. So since u is mostly the 0 signal, x winds up just being the 0 signal. When that spike comes in to u, it is transferred completely over to x, and nothing happens to it until k time steps later, where what is happening is you're looking backwards at what your output signal was k time steps ago, and you're multiplying it by this gain, alpha. And since alpha is less than 1, then you're getting a smaller version of that signal from k time steps ago. And then you go back to 0, and then after another period, you get a smaller version of that initial bump. And this just keeps going and going and going. And that's just like an echo. This is exactly what that recurrence relation is doing. So what now? Well, we've got this matrix. Let's think about what the eigenvalues of this are and how that relates to the effect of this echo machine. So, given that matrix A, it's pretty simple. We should be able to figure out the characteristic polynomial. And indeed we can. You can check that the equation you get is minus lambda to the k plus -1 to the k plus 1 times alpha equals 0. And what that means when we solve it is that lambda is really alpha to the 1 over k, the kth root of alpha. Well, wait a minute. No, that can't be right. I mean, that is right, but shouldn't there be k eigenvalues, k different eigenvalues? Are these, maybe these are all repeated? It seems like I've only got one. No. No. It's time to review a little bit about how roots work. Recall for me, please, the kth roots of unity in the complex plane. What do I mean by that? Well, take the complex plane, real axis, imaginary axis, consider the unit circle that passes through the square roots of 1. That is 1 and negative 1. You know what the square root of 1 is, and you know that there are 2 square roots of 1. But how many cube roots of 1 are there? How many fifth roots of 1 are there? Well, let's think. By Euler's formula, 1 is really the same thing as e to the 2 pi I, or e to the 2 pi I times n for any integer n. Now, if we want to compute the kth roots of 1, we can compute the kth roots of e to the 2 pi I n, and consider how many of those there are. Now, remembering the polar form for how this works, remembering Euler's formula, all that good stuff, that means that really, if we look at the cube roots of 1, there are 3 of them, equally spaced on the unit circle. Aha. What are the fourth roots of unity? Oh, well, that one is actually a little bit more intuitive because, of course, you have not only 1 and negative 1, but I and negative I as well. But notice how these form a regular square in the complex plane with vertices on that unit circle. Does this work for the fifth roots of unity? Does this give you a pentagon? Yes, of course. What about the sixth roots of unity? That works there too? You're getting every 60 degrees? Yes, of course. This is how roots of unity work in the complex plane, as one should have learned quite a long time ago. But, well, too busy studying for AP exams. Okay, so where were we? Given that lambda is the kth root of alpha, where alpha is this real number between 0 and 1, then this really means that we have k eigenvalues, k roots on a circle in the complex plane of radius, the kth root of alpha, where by that I mean the real, the unique, positive, real root along the real axis. All the other eigenvalues are going to be arranged on a circle of that radius. Now, if the total number of eigenvalues is even, then one of those is going to be negative and real. But if the total number is odd, then these are going to be equally spaced around this circle, and all of them are going to be complex except for this positive real root. And that's what the eigenvalues of an echo look like. And that's kind of cool. You're going to want to remember this for use in understanding future systems. Now, there's just a whole lot to think about this. Can you imagine hearing these eigenvalues when you think about what an echo is doing? What happens if you start changing this gain? What happens if alpha is set to 1 or something bigger than 1? Now, why is it that this system doesn't have a dominant eigenvalue and eigenvector pair? We had that when we were looking at population models, and this is kind of like a population model, but oh no, it's not exactly the same because we don't have continuous reproduction. We just have reproduction at the very, very end of a life cycle after a very, very long period K with this window. Very interesting, very much worth thinking about some more.